Hello, everyone. As Gemma introduced, I'm going to talk about tools. In general, ARM software tools that application developers and in particular gaming developers can use. I'm going to give an overview of them, and I will focus mainly on the Mali GPU tools. But I will also introduce the ARM CPU tools. This is a two-parts presentation. The first one is going to be a little bit more like an introduction. I will list all the tools and features, maybe slightly boring. But the second part is going to be practical. I'm going to show how we use these tools to analyze some common applications, for example, Epic Citadel from Epic Games, and also a couple of use cases from Gameloft. So my name is Lorenzo Dalcol. I am the product manager for the Mali GPU tools. I work in the development solutions group at ARM. I was an engineer before, making the same tools I'm going to show you. So I'm still quite connected with the technical aspect. And I believe if you are game developers, there's no need to explain how important performance analysis and debug is. I am sure every one of you knows about improving the performance in terms of FPS, so frames per second, hopefully, if it's not seconds per frame. But I would like to highlight that this topic is becoming more and more important on mobile platforms because users now expect to play the same game they're playing on consoles or PCs, on a tablet or a smartphone, only that these devices have even a higher resolution display than your laptop or your TV. For example, it's pretty common to find 4 megapixels display now on a tablet. They run on a battery, and the ARM IP, like CPUs, GPUs, interconnect, are very power efficient, but they are an enabler for efficient software. So you still have to write good software that actually exploits the features of the ARM IP in order to save energy. Because this is the second part I wanted to highlight, that here we are not just talking about performance in terms of frames per second, but also about energy. There is a straight correlation between the time your gamers spend on your game and the in-app purchases they do. So basically, the more they play, the more they spend, and the more your company or you gain. So you surely don't want the battery to run out in like an hour. The first tool I'm going to present is the ARM DS5 Development Studio. This is the only tool that also comes as a commercial tool, while all the others I will be presenting today are free of charge. But there's also a community edition for DS5 called DS5 Community. It's free, even for commercial usage. It's just limited. You can do all the GPU performance analysis with it, but you can't do like CPU profiling. So what is DS5? Well, it's a full IDE based on Eclipse. It comes, if you buy the commercial edition, it comes with the professional ARM compilers. So the ARM compiler 5 and the ARM compiler 6 that supports ARM v8, so ARM 64-bit. It also comes with our debugger, so you can actually debug every ARM CPU. And here we are talking about hardware debugging, probably a little bit far beyond games, but basically if you have any ARM device, even the chip that is inside your car or your washing machine, you can debug it with this tool. But then there is a tool inside DS5 which is called Streamline, a performance analyzer, which is the one I'm going to cover in detail today. It's a profiler. It shows charts of the activity going on the whole system. So not just the GPU, but also CPU, memory, network, Linux kernel, and so on. It's time-based, but also event-based. So it's a sampler, but also an event-based profiler. You will see later quite a lot of it. I've mentioned the debugging capabilities of DS5. I'm not going to spend a lot of time on it because I believe you all know how to set a breakpoint and step through lines. I would just like to remind you that you can do that with DS5 on both Linux and Android targets, also with C++. You don't need a separate hardware to do that because we also have a user space debug version that just uses a TCP/IP connection over Ethernet or a DB to connect to the GDB server and get the debug information. Now I'm going to present the graphics tools, which are the tools I manage and my team of engineers develops. The first one that we are putting a lot of effort on is the Mali Graphics Debugger. It is an API tracer, quite advanced tracer. It captures all the API calls for OpenGL ES 2, 3, and now we are making a 3.1, but also OpenCL and EGL. I call it an advanced tracer because you don't just see basically the API calls, but you actually get all the data that is being used around these API calls. So all the buffers, even server-side buffers, shaders, textures, and even some information coming from the driver. I have already introduced ARMDIS5 Streamline, so I'm going to jump to the next, which is the Mali Offline Compiler. So this tool is a command line tool that runs on your desktop machine, so Windows or Linux or Mac. It is the same Mali shader compiler that is inside the Mali driver that you will have on your phone or tablet, only that is compiled for x86 machines. So this tool does two things. It compiles shaders to the binary format, which can be useful, but it's a little bit tricky because then you need a lot of binary formats for each GPU vendor and so on. But if you want, you can do that. But it also does static analysis. So it will tell you how many instructions for each pipeline, so texture, load and store, arithmetic. So it will tell you how many instructions your shader will generate, and also how many registers have been used. So it will tell you, for example, if your shader will do register spilling, so it will have to go to memory because there's not enough available registers, and that is a terrible thing. And it will also tell you how many instructions are generated. If you don't have cycles with a dynamic number of iterations, the number of instructions will hopefully be the number of cycles that your GPU is actually executing for that shader. But of course, it also depends on the memory accesses and the cache hit and miss ratio. So this is static analysis, very useful, very fast, but we will have to use Streamline to also see what's going on dynamically. Other tools we make available on our Mali developer website are the OpenGL ES emulator. So this is a OpenGL ES library, again, for your desktop machine that will emulate OpenGL ES on desktop. So it's actually using the underlying OpenGL driver, so your GPU, your desktop GPU, to execute your graphics commands with OpenGL ES instructions. We put a lot of effort to make it Chronos conformant. We usually achieve conformance on a particular machine, and it runs pretty well on almost every other desktop that has got OpenGL. This can be useful to do development, early stage development. You can easily configure your application to build for your desktop machine and the emulator or the actual target. Another tool we have is the texture compression tool. Again, it comes with two components. One is the command line and one is the GUI. So I believe someone this morning talked about ASTC, the new texture compression format, the standard compression format. The texture compression tool has got an encoder for that, and also the previous standard formats like ETC and ETC2. The command line tool can be embedded in your build system to compress all the textures. For example, when you make a release build, you can usually set which speed you want and which quality of image you want. And the GUI will actually show you the difference between the uncompressed texture and the compressed textures. So you can zoom in and see if a certain bit rate is enough for your textures. Because these compression formats are lossy. Finally, we also allow integration with third-party tools. So you can integrate the command line components with your system, as I said. If you do it internally, your company, we are very happy. And if you want to give us feedback or bug reports, we are happy to work with you. If you want to redistribute a tool with these components inside, we are usually very happy to do that as well, but you need a license, so you need to contact us, and we will work it out with your company. So the workflow, when it comes to performance analysis and debugging, it's this for graphics. So we usually analyze the game using Streamline. So we get all these nice charts showing basically every part of the hardware and software, how busy they are, if there are cache misses, if the GPU is stalling, waiting for memory. And then this is to identify what the bottleneck is. Then we use the Mali Graphics debugger to understand why some bottleneck is happening. For example, Streamline is telling us your vertex shader is really slow, there's a lot of cache misses. Then we switch to the Mali Graphics debugger, and it will actually show that some draw calls have a crazy number of vertices, and they're also sparse in memories, and so basically the GPU has to access them in a non-very convenient order. Then, if a problem is in the vertex shader or the fragment shader or the other types, we can use the Mali offline compiler to optimize the shader code, and then we iterate. A lot of ARM partners are actually using these tools, and they are obtaining very good results, sometimes even doubling the frames per second, so we are really happy about that. I think I've talked enough about the Mali offline compiler. I forgot to mention that we support every revision of our driver in it, and also every hardware core that has been released. So from Mali 300, 400 to the Mali T760, which is the latest one. When you run the command line tool, you can pick which hardware core, which driver revision, and you actually get the statistics for that one. So in your nightly build, for example, you can run it on different variants, and you can see if there is a regression on one of them. One other collection that we make available is the Mali SDK. So this is an OpenGL ES sample set that runs on the emulator or your target device. We have one for Linux targets and one for Android targets. And the SDK itself is available for Linux, Mac, and Windows. So this is an environment to develop OpenCL and OpenGL ES applications. The sample code is well commented. There are tutorials and step-by-step tutorials to teach you how to implement a certain technique. We also use this to develop shaders. At this point, I'm going to talk about a little bit more in detail about the tools that I have introduced, starting from DS5 Streamline. So this tool has got a timeline showing hardware counters, software counters, and events. The hardware counters come from the ARM Cortex CPUs, and for example, they can be the number of cycles, the number of cache misses, how the pipeline is behaving, and you can even correlate CPU counters to the source code. I'm going to show you a demo later. Then we also have support for the Mali GPUs, again, hardware counters coming from the hardware. So when the GPU is running, it's collecting data like how many load and store instructions is running, how many stalls, how many textures have been, texture fetches, sorry, have been decompressed, and so on. There's more than 300 Mali GPU counters that you can choose from. We also have software counters, that's how we call events that come from the driver stack, and even the kernel stack. We also support custom counters, which are basically the component that's collecting all this data is open source. It's called Gator. I think I have a slide for it, yes. So usually your system will have your applications and your middleware. If they use graphics, they will talk to the OpenGL ES library and the Mali driver. If they don't use graphics, they will go directly to some system calls and the Linux kernel eventually. And finally, this will run on ARM processors. So we provide this module called Gator that has to be installed on the system in order to expose all the data to Streamline, to the host application. This module comes with a kernel space module, so gator.ko, which is to access all the low-level information for all the processes, so basically the whole system, and a user space Gator, which is a daemon, a simple process that you run, and that interacts with the GUI, with Streamline, and also with the kernel module. If you can't make kernel module because you don't have access to the kernel, now we support user space only profiling, so you just need the Gator daemon, and it will use perf to get stats out of the Linux system. The user space only solution doesn't support the GPU yet. So I was saying the Gator source code is available, and it's actually a pretty small piece of software. So you can even modify that and get some custom counters from other drivers that you have access to, or basically anything that's memory mapped can be read and passed through Streamline, which will visualize it. The other features of Streamline are more common. So there's a call paths view, a functions view, and the code view. At this point, instead of showing you some boring slides, I will actually run the application. Hopefully you can see. Otherwise, I can zoom in a little bit. So on the top panel, you have all the charts with the CPU and GPU activity in green there. You can open up the CPU and see the different CPU cores. In this case, this was run on a Nexus 10, so we have 2 Cortex A15. But I think I also have an example that was captured on a big. LITTLE device. So a device with 2 clusters of CPU cores, 3 Cortex A7 and 2 Cortex A15. So if I open up the CPU activity, I see the 2 cluster, and if I open it even more, I can actually see the 5 cores. Down at the bottom, it should tell me what they correspond. I need to go to the class, to the core map. Here we are. It's probably a little bit small. Yeah. So it's telling me the cores 01 and 2 are Cortex A7, the other 2 are Cortex A15. Since I've just used, I will also talk about the bottom view. So by default, the bottom view will show me a heat map of the processes and threads that are running at that time on the system. I can open up a process and see the individual threads. A nice thing is that if I select a process or a thread, all the other charts will actually highlight the activity that is going on just on that process or even just on a single thread. Here we are. Not just the top activity, but also the other CPU counters that we have. So for example, in this case, I got branch mispredicted, the bus access, the L2 cache accesses, the frequency and the cycles of the CPU. Even the frequency can change, the number of instructions that are executed, and so on. The bottom view also supports other kind of views. So there's a cluster map which shows if the big or the little part of big little is being used. If your application uses only the little cores, it will run for longer because they are more power efficient than the big ones. But it's quite usual that you have some spikes for just a few milliseconds going to the big cores. Other views that we have are the processes view, which is actually just a report showing me which process was more active during the execution. And the OpenGL view, which is on a different example. Here we are. I don't know how familiar you are with OpenGL, but basically here we have a view that shows the OpenGL kernel executions, the memory sinks, and even the dependencies between them. It's quite useful because we can correlate that with what's going on the CPU counters. Going back to my presentation. So other features of Streamline are the events. So everything that I've showed until now works on any application. But if you want to know, for example, what is going on at any point inside your game, you can write some simple annotations. They're very similar to a printf, only they go inside Streamline. And they will visualize as events in the same timeline. We even support graphics annotations, which are basically images. We can get the frame buffer out of the Mali driver. Of course, it can be quite big, so in that case, some of the activity going on the CPU will actually be just to generate, to transfer the frame buffer. But you can even output textures or anything, basically, that you have control on. This is the performance chart configuration panel, where you can choose more than 40 CPU registers, more than 300 Mali registers, and so on. And before I switch to the Mali graphics debugger, I would like to show you the energy-based analysis. So I've mentioned how important it is to save energy and to basically make your game run longer. There are ways to do this analytically. We have a little USB dongle, which is called ARM Energy Probe. It's a lightweight and cheap way to measure energy and power of your software. Basically, you have to connect this dongle with some wires to a development board. It even works with cheap development boards like the Andel board that we have. You can monitor up to 3 probe points at the same time. And Streamline automatically correlates the energy data with the CPU activity. We also have support for a more professional solution, which is the NI DAC, the National Instrument DAQ. And this is a slightly more expensive device, but not too much. It supports up to 40 analog inputs. So if you have, you can basically connect it to the display, to the CPU, to the GPU, to the battery, and see different charts. I'm not an electronic engineer, but I am told it's pretty easy to plug this. You just need a shunt resistor, and basically it will work. What I have done though was using it. It's actually quite interesting because you can see the energy going up and down depending on your software. You can also track the VFS, so the dynamic voltage and frequency control scaling. So again, if you want your application to run for a longer time, you can track that. At this point, I'm going to talk about the Mali Graphics Debugger. It's a complementary tool to DS5 Streamline. The DS5 Streamline is for profiling, while Mali Graphics Debugger is for debugging. It has an overhead because it's transferring over USB or Ethernet all the buffers and arguments that you're sending to the OpenGL ES driver. So it can be quite a lot of data. But again, it's not used for profiling the application, it's used for debugging. So to debug, you actually need access to all the data. The way it works is that it captures all the API calls, and they are shown in the middle as a very long list. They can be millions. Since surfing over a million calls is hard, we have actually built an outline view on the left, which shows individual frames and draw calls. The new version will also show different render targets. So since draw calls are probably the most important API call in a game, you can easily select them there and see how many vertices and how many fragments they are shading. In fact, you can actually select any API call in the center view, and the rest of the application will update to show the state at that point in time, not just the GL state like GL blend or GL clear color, but also the state of all the assets, which means textures, buffers, shaders, uniforms, vertex attributes, and so on. So, for example, if you identify that one object in one frame wasn't really drawn in the right way, or there was a glitch, you can go there, select the draw call, or select some previous call and see what was going on at that point. We also have a dynamic help view on the bottom, which will detect automatically GL errors or other warnings. For example, if you're not using vertex buffer objects, or if, I don't know, the access to some data is not convenient for the driver. Both Streamline and the Mali Graphics Debugger work in this way. You need a target, which is Android or Linux. You install a daemon. In the case of the Mali Graphics Debugger, it's called MGD daemon. It works in user space only mode, so you don't need to fiddle with the kernel. And then you can connect to basically any kind of host operating system to debug. I will spend some time showing you how we used the Mali Graphics Debugger in the second part. Before that, I would like to show a slide that shows how we have implemented it. So there is an interceptor library which stays between your application and the OpenGL ES, EGL, OpenCL drivers. We generate this interceptor library to have all the entry points of the said APIs. So the application basically will see this interceptor library just as any standard driver. Only that we capture the calls and their arguments, and we send them out to the Mali graphics debugger. Then we also call the other libraries, the actual libraries, to run your game. This interceptor library is actually very lightweight if you're not capturing data. So it can stay on your system. It's basically just one additional function call every time you call a GL API. Once you enable the Mali graphics debugger, it will start transferring data. In that case, it can be heavyweight, depending on your application. So, as I said, I will cover both tools in detail after the break. But if you have any question now about what I've presented, I'm happy to answer those. Yeah.
Does the emulator support the ARM extensions, like flex and that stuff?
So the emulator supports some extensions. For example, we support the mobile text-to compression formats as ASTC or ETC. There were another couple of extensions that we support. I don't remember exactly which. It doesn't support pixel local storage, for example, because it's a little bit hard for us to emulate on a desktop machine, since that extension is available on Mali hardware, but not on the other. Are you interested in a particular extension?
Yeah, that on free buffer flex.
Yeah. For the fetch one, I have to check. Anyway, if you have any question about the emulator or other tools, you can ask on our community website. We answer every day. Yep.
So if you're doing compute shaders, transform feedbacks, or you're just writing to frame buffers, is it downloading all those buffers from the GPU?
So yeah, good question. Since downloading every frame buffer or every buffer after every API call would be too much overweight, heavy basically, we have a frame capture button which you can press, and that will do a full capture of one frame. In that case, yes, it will capture every buffer, but it can take a minute or two for one frame, so it's quite long. But after that, you have access to all the data. So before you ask another question, I will actually answer a question that was asked a few sessions before. I thank our Google friends for their session. That was really good. That was a question about whether ARM or the market are developing a lightweight OpenGL API. So there was an announcement from Kronos. Actually, one of our colleagues from ARM is the chairman for OpenGL ES in Kronos. And at SIGGRAPH this year, he announced there is a working group for what they call, at the moment, OpenGL Next Generation. There's not a lot of information publicly available. It says it will be closer to the hardware and lightweight. There will be an intermediate unified shader language for the different shaders. And yeah, I'm not sure there's a lot more available publicly. You can Google for it.